Hello, it's .134, Lecture 7. Last time we discussed the Poisson approximation to binomial, and we saw that the Poisson mu is a limit of binomials for n goes to infinity, p goes to 0, and n times p goes to mu. So you can learn a lot about the Poisson from the fact that it's a limit of binomials. So for example, you know that the mode of the binomial np is the floor of np plus p, and that the mode is either m if np plus p is not an integer, or m minus 1 m if np plus p is an integer. Well, if you convert this to Poisson by thinking of np going to mu and p going to 0, then you see that the mode is the floor of mu if mu is not an integer, and m minus 1 and m if mu is an integer. And so here's a picture of the Poisson for different mu's. When mu is 1, you can see that you have two modes, as you do when you have mean 5 or 10, and that all follows from above. So today we're going to talk about random sampling, both independent trials and dependent trials. When you have independent trials, this will give us the binomial distribution and the multinomial distribution. The binomial distribution has 2 outcomes. The multinomial distribution has k outcomes, where k is greater than or equal to 2. For dependent trials, we'll have the hypergeometric distribution with 2 outcomes, and multivariate hypergeometric with 2 or more outcomes. So, for example, let's say that we have a class of 100 students, and the grade distribution is as shown here. So if you sample 10 students with replacement, what's the chance that you get 4 A's, 3 B's, and 2 C's and a D in that order? And what's the probability that you get 4 A's, 3 B's, 2 C's, and a D? Well, remember that we're drawing with replacement, so the chance of getting an A is 1/2, so we get 1/2 to the 4th. And the chance of getting a B is 0.3, so we get times 3.3 to the cubed, and so on. Now, when you want to find the probability of 4 A's, 3 B's, 2 C's, and 1 D in any order, then we know that we have 10 factorial permutations of 4 A's, 3 B's, 2 C's, and a D above. But the 4 A's are interchangeable, as are the 3 B's, 2 C's, and a D. So we need to divide by 4 factorial, 3 factorial, 2 factorial, 1 factorial. And each permutation has the same probability, namely 0.5 to the 4th, 0.3 cubed, 0.15 squared, and 0.05 to the 1. We can write 10 factorial over 4 factorial, 3 factorial, 2 factorial, 1 factorial as 10 choose 4, 3, 2, 1, which, by the way, is the same as 10 choose 4 times 6 choose 3 times 3 choose 2 times 1 choose 1. So the definition of the multinomial distribution: if you have n independent trials where each trial has k possible outcomes, a1 to ak, with probabilities p1 to pk, as shown here, then the probability you get n1 outcome a1 out to nk outcome ak is n choose n1 to nk times p1 to the n1, p2 to the n2, pk to the nk. So this just generalizes what we just did above. Once again, the binomial distribution is a special case with k equals 2, and we've been dealing with the case where we have independent trials. Now we're going to turn to when we have dependent trials, which we called random sample without replacement. So in a very student-friendly class with 100 students, the grade distribution is 70 A's and 30 B's. You sample 5 students at random without replacement. This is called a simple random sample, or SRS. Find the chance that you get 3 A's and 2 B's. Find the chance that you get find the probability that you get 3 A's and 2 B's. So here, because we're drawing without replacement, after the first A, there's only 69 A's left out of 99 students. So, and continuing this way, we get the answer shown. Furthermore, so all reorderings of 3 A's and 2 B's in different orderings gives us there are 5 choose 2, 3 ways to do that. In other words, 5 factorial, 2 factorial, 3 factorial. So now, as some of you remarked, we can write this a different way. So if we write this number, if we just rearrange things and put the 3 factorial under the 70, 69, 68, and the 2 factorial under the 30, 29, and the 5 factorial under the 100 down to 96, you see that you get 70 choose 3 times 30 choose 2 over 100 choose 5. This is the hypergeometric formula. And it says the bottom is choose 100 out of 100 students, choose 5. Of those 5, 70 of the A's in that 5, 3 get A's, and of the B's, there are 30 B's, there's 70 A's, 3 of them get A's, and of the B's, 2 get B's. So the hypergeometric formula, general definition, suppose a population of size n contains G good and B bad elements, where n is G plus B. A sample size n with G good and B bad elements, n is G plus B, is chosen at random without replacement. The probability that you have G good and B bad is this hypergeometric formula shown here. So notice that the capital G and the capital B add up to the capital N in the denominator, and the small g, small b add up to the small n in the denominator. So this generalizes to the multivariate hypergeometric, where now instead of 2 types of elements, we have k with sizes g1 to gk. And so in our sample, we have n is g1 to gk. So the probability of getting G1, G2 up to GK is given by this generalized hypergeometric formula shown here. So for example, in our first problem, where we had 100 students with a grade distribution, but we were drawing with replacement, now we're going to draw without replacement, find the probability that we have 4 A's, 3 B's, 2 C's, and 1 D. So this will be 50 choose 4, 30 choose 3, 15 choose 2, 5 choose 1 over 100 choose 10. Noticing that all the 50, 30, 15, 5 add up to 100, and the 4, 3, 2, 1 add up to 10. So here's some questions then that we did. So a 5-card poker hand consists of a SRS of 5 cards from a 52-card deck. There are 52 choose 5 poker hands. Now find the probability that a poker hand has 4 aces and a king, that a poker hand has 4 aces, the poker hand has a 4 of a kind, which means that you have 4 A's and a B, where A and B are not the same. So, so here, the poker hand has 4 aces. So we have 4 aces, of which we choose 4, 4 kings, of which we choose 1, and 44 non-aces or kings, of which we choose 0, divided by 52 choose 5. Now 44 choose 0 is obviously 1, so you don't have to write it, but just for pedagogical reasons, I wrote it here. Furthermore, find the probability that the poker hand has 4 aces. One way to think of it is that we have 4 aces, of which we choose 4, and 48 non-aces, of which we choose 1, over 52 choose 5. Or you could think that I have 4 aces, of which I choose 4. I choose another rank, 1 of 12, and then whatever that rank is, I choose one of those. So, yeah, these are the same. If I want to find the chance of having a poker hand that is a 4 of a kind, so here you can think that I have 13 choices for A, so out of 13 I'll choose one A. Of that, there are 4 of that rank, of which I'll choose 4, and then 48 non-A's, of which I'll choose 1, over 52 choose 5. Or another way to think about it is I have 13 choices for rank A, 12 choices for rank B, and I'm getting all the A's and 1 of the B's. So then we did a concept test. So the probability of being dealt a 3 of a kind poker hand ranks AAA, B, C, where A is not equal to B, is not equal to C, is which of the following? So here the answer is B. So the reason is that, so we're going to choose our rank for A. There are 13 choices. And now there are 2 singles, and those 2 singles are interchangeable. In other words, AAABC is just the same as AAACB. So the two singles I'm going to choose 2 ranks for. So out of the 12 remaining ranks, I'm choosing 2. And now my A, B's, and C's are chosen. So I've separately chosen the A's from the B, C's because the A is distinguishable from the B's and C's. The A's are 3 of a kind, whereas the B's and C's are singles. The singles are interchangeable. The A's are the 3 of a kind is different than the singles. So I have, once I've chosen my A, B, and C, then it's just I have 4 choose 3 for the A's, 4 choose 1 for the B's, and 4 choose 1 for the C's, over 52 choose 5. So just to sort of generalize this, if say that I had an 8-card poker hand with 2 3 of a kinds and 2 singles, then you'd have 13 choose 2, 11 choose 2, right? Because in front, right? Because I'd need to choose 2 ranks for my 3 of a kinds and 2 ranks for my singles, because the singles and the 3 of a kinds are distinguishable, but the 3 of a kinds are not distinguishable from one another. So then we did another problem. The probability of being dealt a pair in a poker hand ranks A, B, C, D, where A is not equal to B, is not equal to C, is not equal to D is, and the answer was C. Okay, so here, again, the pair is distinguishable from the singles. So I have 13 choose 1, 12 choose 3, and then 4 choose 2, 4 choose 1, 4 choose 1, 4 choose 1, over 52 choose 5. So, and I've just written here again that the reason that we're taking 12 choose 3 is because B, C, D can appear in any order here. I don't distinguish these because in my poker hand I don't distinguish the order of the singles. Okay, so I'll be interested to see what your responses are to this. Have a great day. I'll see you next time.